All right, folks, welcome. A video today on linear independence in spanning sets. So we'll start with recalling our definition of linear independence. We'll see an example of linear independence in a couple of different vector spaces. We'll see an example of linear dependence as well. We'll then talk about spanning sets and talk about a vector representation in any vector space. So these definitions should be familiar. If V is any vector space, and we have a set of vectors u1 out to un from that vector space, a vector equation of the form alpha 1 u1 plus alpha 2 u2 out to alpha n un equal to 0 is a relation of linear dependence on S. Of course, one way that we can make this equation true is the trivial relation of linear dependence, all of the alphas equal to 0. If there's a non-trivial relation of linear dependence on a set S, we say that that set is linearly dependent. If the only relation of linear dependence on a set is trivial, then the set is linearly independent. So here's an example, sort of an unfamiliar example, but an example of vectors from P4. So I'm going to call these vectors P1, P2, and P3. Okay, I'll let you verify that 3P1 plus 4P2 minus P3 is equal to the 0 vector. So we see then that S is linearly dependent. Okay, similarly, we'll go ahead and show that this set of vectors is linearly independent. So we'll do that by having a look at a relation of linear dependence on this set T, which I'm saying the set T is Q1, Q2, Q3, and Q4. Okay, so of course the way we do that is by expanding out alpha 1 Q1 plus alpha 2 Q2 plus alpha 3 Q3 plus alpha, this should be alpha sub 4 Q4. Okay, and when you do that, it's sort of messy, but of course this polynomial on the left-hand side is just a quartic in disguise. So we can organize up by powers of x instead, and when you organize up by powers of x instead, you get something that looks like this. Okay, so there's a coefficient times x to the fourth, plus a coefficient times x to the third, plus a coefficient times x squared, plus a coefficient times x, plus a coefficient times x to the 0 that's equal to 0. Now, of course, we know that the only way for the thing on the left to be equal to 0 is if all of the coefficients are equal to 0. So it has to be, therefore, that there's some linear system in these alphas that's satisfied for this system to be 0. Okay, so here's that homogeneous system of equations again, and we can identify the coefficient matrix. Once you identify the coefficient matrix, it turns out that that coefficient matrix reduces to the identity. The only relation of linear dependence is trivial, so the set T is linearly independent. And okay, so here's an example for you to work on. I hope you remember the crazy vector space C, where we have unusual definitions of vector addition and scalar multiplication. So I'll go ahead and have you investigate whether 1063 is linearly independent in the crazy vector space. Okay, let's talk a little bit about spanning sets. So here's sort of a new definition. A subset S of V is called a spanning set of S if the span of that set is equal to V. Okay, I want to point out that this statement S equals V is a statement of set equality. Now, we've dealt with set equality before, and what you have to do to show this set equality is to show that the first is a subset of the second. That's usually pretty straightforward because most of the time all of the elements from S come from V, right? So any linear combination of those elements are from V. But then you have to show that any arbitrary element, say vector V from the vector space V, is in the span of S. Okay, so that's a little bit more difficult, and as usual, this involves showing some linear system is consistent. So I'll let you work this out on the worksheet, but we'll sort of walk through it together. we're going to show that this set S is a spanning set of the subspace W we talked about last time, right? So this subspace W is the subspace of P4, where all of the vectors all of the polynomials, when you plug in 2, you get out 0. Okay, so we can pretty quickly see that all of these elements of S are elements of W, right? When we plug in 2 to this x minus 2, we get 2. When we plug in 2 to this one, it turns out we get 2. When we plug in 2 to this one, it's a little more work, but we also get 2. And when we plug in 2 to this one, it turns out, lo and behold, we get 2. Okay, so since any element in the span is a linear combination of those elements, whenever we plug in 2, we're going to get 2 for any element of the span. Okay, so everything in the span of S is in W. Okay, now we're going to argue that anything in W can be written as a linear combination of elements of S. So anything in W is also in the span of S. Okay, so in order to do that, we're going to go ahead and choose an arbitrary element R that's in W, right? So whatever R does, it follows the rule to be in W. And the rule to be in W is that when we plug in 2 to R, we get out 0. Okay, so R is an arbitrary element. Maybe R is something like a x to the 4th plus b x cubed plus c x squared plus dx plus e, right? So whatever R is some quartic. Now, as it turns out, and you'll have to work this out, when we go to write R as a linear combination of the elements in S, we come up with a non-homogeneous linear system. Now, this non-homogeneous linear system is a little bit annoying, but at the end of the day, when you identify the coefficient matrix in row reduced or reduced row echelon form, it turns out that you get this matrix. Okay, so there's one possible problem here, and that one possible problem is a question of whether this element is 0, right? Because if this element is 0, then our system is consistent, and we see that R can be written as a linear combination of the vectors in S. Now, as it turns out, because R satisfies the rule to be in W, when I plug in R of 2, I get exactly this expression. Okay, so I'll let you work that out for yourself, but it turns out that when R is in W, that expression has to be 0, and that gives us that S is a spanning set of W. Okay, here's another example. The set of all 2x2 matrices that satisfy these two rules. Okay, so it turns out we're going to identify a spanning set for this subset Z. It's definitely a subspace, right? Because we can see that there's some homogeneous linear system that we can recast this subset Z as. Okay, so we'll find a spanning set. Okay, so again here we sort of recast X as an element of Z if AX is equal to 0 for some X equal to A, B, C, D, and this matrix A that is what we would get from picking off those coefficients. Okay, so one thing we can quickly do is reduce A to its reduced row echelon form. Okay, so when we reduce A to its reduced row echelon form, we can see pretty quickly that that reduced row echelon form has two pivots. We can identify the span of vectors that gives us a null space, right? So those vectors are -3, 1, 0, 0, and 1, 0, -4, 1. So we can quickly see, therefore, that this set tells us a spanning set for this set Z. Okay, so just translating that vector X in C4 into 2x2 matrices, we see that a spanning set for Z is -3, 1, 0, 0, 1, 0, -4, 1. Okay, cool. I'll let you work this out on the worksheet, but we previously saw that this set turns out to be linearly independent in the crazy vector space. It turns out that it's also a spanning set. Okay, so the way you have to do that is show that an arbitrary element of C can be written as a linear combination of those two vectors, where vector addition and scalar multiplication is defined in the crazy vector space. So I'll let you work that out, but this is a pretty cool exercise in the crazy vector space illustrating a spanning set. Okay, so the last thing I want to talk about is vector representation. One thing we can do is think about a set that is a set of three vectors here. This is just an example, and we'll argue that the span of this set is all of C3. So the way we'll do that is, again, by the set equality. Certainly anything in the span of S is an element of C3. Okay, again, usually that first part is pretty straightforward. However, any arbitrary B that's an element of C3 has B in the span of these set of vectors. And the reason for that is because these vectors are the vectors associated with the coefficient matrix for archetype A, and we know that archetype A has a coefficient matrix that's non-singular, right? So the linear system LSAB always has a unique solution. Therefore, we can always write B as a linear combination of the vectors in S. Okay, for instance, this vector B, negative 33, 24, 5, has B equal to minus 3 times the first vector. This first vector, here I'm calling this one V1, V2, and V3. So minus 3 V1 plus 5 V2 plus 2 V3. And we call minus 3, 5, 2 the vector representation of B relative to the set S. Okay, this is going to come up later, being able to represent a vector as a vector representation of a span. Okay, so it turns out that when B is a linearly independent set that spans a vector space V, and W is any element of V, then the vector representation is unique. Okay, so to prove this, and this is a pretty cool proof, what we do is assume that there are two such vector representations and then show that they're the same. Okay, so here are those two vector representations. Maybe W has a vector representation with the A's, and W has vector representation with the B's. Now, of course, one thing we can do is think about the difference of those vector representations, which ought to be the zero vector. Okay, so here's that difference. The first representation, W, minus the second representation of W ought to be the zero vector. Now, what I'm going to do is recollect these up in terms of the V's instead. So here's that vector equation, which happens to be a relation of linear dependence on the set B. Now, since the V's are linearly independent, it must be that each coefficient is 0, therefore A1 is B1, A2 is B2, and so on and so forth. Okay, so this it ends up being a pretty cool property of any linearly independent set that spans a vector space V, that the vector representation of any element W and V relative to that set B is always unique. Okay, so we'll see that a little bit more later when we talk about bases. It turns out that this is a basis for V. All right, folks, that's it for this section on linear independence and spanning sets. Have a great day, and we'll see you next time. So long for now. Bye-bye.